we're going to do one more thing here with the first derivative before we move on to the second derivative, which is to talk about how to use the first derivative to find a tangent line. So a tangent line is just a straight line that touches the curve at this point here. We want to touch at a specific point. So in this case, what we want to do is use the equation of total cost from the previous example to find the line tangent to the curve at q equals 2. That's a great tangent line. It's going to be a little closer than that, right? So here we want the line that touches the curve at q equals 2. And at that point, this straight line and the curve will have the same slope. So that's going to help us find the equation for this tangent line, because I know the slope of the curve is equal to the marginal cost. So what is the marginal cost for this firm at q equals 2? You just, like we did before, plug in 2 to your marginal cost equation, and we see that the slope here will be equal to 40. Now, the last thing we need to do to find the equation for this line is to find the y-intercept, right? It's a straight line, so it's y equals mx plus b. I just need to find the slope and the y-intercept. So here, I know that the slope is 40, and I know I can plug in quantity of 2, total cost of 50, because I know that the line has to pass through that point. So if I plug those numbers in, then I can solve for b, or the y-intercept. That's 80 plus b, so b has to equal -30. And this equation then for my tangent line will be this. Y equals 40 cubed minus 30. Now on to second derivatives. To find the second derivative, we're really just taking the derivative of the first derivative function. So it's not really too much new here. If we want to find the second derivative of this function, again, we'll start with the first derivative. And then we just take the derivative again. And I get that the second derivative is equal to 20. What does that tell me? It tells me that the slope of the function is increasing. In other words, that the total cost function, I know it's increasing because the first derivative is positive. And I know it's increasing at an increasing rate because the second derivative is positive. So the sign of the first and second derivative tell me about the shape of my original function. It's increasing at an increasing rate. And that's what we call convex. For an increasing function, convex looks like this, going up faster and faster. The opposite of that is called a concave function. And it looks like this. It's increasing at a decreasing rate. I like to remember the difference between these two because the concave function really looks like a cave, right? The last thing I want to review in this section is how to find partial derivatives. So far, we've just used functions with a single variable, q. But in many examples, we're going to need to take the derivative of functions with lots of different variables, and we need to do that using partial differentiation. You can also use total differentiation, but we're not going to do that so much in this class. We're going to focus here on partial derivatives. Partial differentiation is actually pretty simple. All you do is ignore the other variable. So I've got this function here. 6x times y cubed. And I want to take the derivative both with respect to x and with respect to y. So if I take the derivative of my function with respect to x, you can write that as in this way, the derivative with respect to x, or you could write that f prime sub x. All I'm going to do is just ignore that y cubed, like it's a constant, and I've got 6y cubed. The x drops out as I take the derivative. Likewise, when I take the derivative with respect to y, f prime y, now I've got to ignore the x, so I've got a 6x as my constant, and then I take the derivative with respect to y, I get 3y squared, so at the end of the day I've got 18xy squared. All right, that sums it up for the math review.